Hey everyone, and welcome. Today we're going to dive into something that sounds kind of crazy, how a machine learning model that seems perfect can actually be totally broken. We're going to pull back the curtain and look at the beautiful hidden geometry that stops our AI from just, well, cheating, and helps it to actually learn. Let's get into it.
So, let's kick things off with a little thought experiment. Picture this. You've just spent weeks, maybe months, training a new model. You run it on your training data and bam! 99% accuracy. You're ready to celebrate, right? Well, hold on. That model, despite its amazing score, might be completely useless out in the real world. So, how is that even possible? This question really cuts to the core of one of the single biggest hurdles in all of machine learning: generalization.
You know, the whole problem really comes down to these two classic failure modes. On one side, you've got underfitting. That's pretty straightforward. Your model is just too simple. It can't even figure out the basic pattern. But the real trap, the more sneaky problem, is on the right, overfitting. That's our 99% accuracy model. It aced the test because it didn't learn the subject. It just memorized the answer key. The second you give it a new question it hasn't seen before, it completely falls apart.
So what's the fix? Well, we can actually look to a principle that's been guiding science for centuries: Occam's razor. It's this beautiful idea that all things being equal, the simplest explanation is probably the right one. For us in machine learning, this is our North Star. We want to find a model that's complex enough to get the job done, but not a single bit more. We need a way to actively push our models towards simplicity to keep them from just memorizing everything.
The cool thing is, this isn't just a philosophy. We can actually build this preference for simplicity right into our math. This whole strategy is called regularization. You can think of it as a kind of penalty. We're adding a tax to the model for being too complex. And the main tool in our toolbox for measuring and penalizing that complexity is a mathematical concept called a norm. Okay, so how do you actually measure something like model complexity with math? Well, we do it with this function called a norm. In a nutshell, a norm takes all of a model's weights, which we can think of as one big vector, and it spits out a single number that represents its size or its length. By telling our model, hey, I want you to learn, but you also have to keep this overall size number as small as possible, we are, in effect, forcing it to be simpler.
Now, while that general LP formula looks a bit abstract, in the real world, we pretty much always use one of two types. On the left, you have the L1 norm. It just adds up the absolute values of all the weights. It's often called the Manhattan distance, like walking city blocks. On the right is the L2 norm, which is the good old Euclidean distance you learned in school, the straight line path. It's the square root of the sum of the squares. And believe it or not, this tiny difference in the formula leads to wildly different geometric shapes and behaviors.
Let's try to visualize this, because this is where it gets really cool. When we use an L2 norm to regularize, we're basically drawing a circle around the origin and telling our model, listen, find the best possible weights you can, but you are not allowed to go outside this circle. That sum of squares formula naturally carves out a perfectly smooth, round boundary. The best regularized solution is found right where the model's own performance landscape just touches the edge of that circle.
The L1 norm, on the other hand, makes a totally different shape. Because it's using absolute values, not squares, the boundary it creates has sharp points and flat edges. It looks like a diamond or a square tilted on its side. And this geometric difference is everything. Those pointy corners actually encourage the model to set some weights to exactly 0, which is super useful for feature selection. But that's a whole other story. For today, we're sticking with the smooth, elegant geometry of L2.
And this is where we get to the heart of it. Using that L2 penalty is so common, so fundamental that it has its own name: weight decay. For a long time, people just thought, oh, it just makes all the weights smaller. But the truth, the real geometric story, is so much smarter and more beautiful than that. We're about to decode what is actually going on.
Okay, I know what you're thinking. This equation looks intense, but I promise you it tells a remarkably simple and elegant geometric story. This is the secret recipe. It shows us exactly how to get from our original, perfect but overfit weights, the W star, to our new, regularized, and much more useful weights, the tilde W. To get it, we just have to read it not as symbols, but as a set of instructions.
The key that unlocks that whole equation is a concept from linear algebra called eigendecomposition. It sounds complicated, but the idea is simple. You could take a special kind of matrix, like the Hessian, which describes the curvature of our model's error surface, and you can break it down into its fundamental components. You get Q, a matrix of eigenvectors. Think of these as the primary directions, the axes of the curvature. And you get lambda, which contains the eigenvalues, numbers that tell you how much curvature there is along each of those axes.
So let's read our equation like a three-step process. Step 1, we multiply our original weights by Q transpose. All this does is rotate our weight vector so that it's perfectly aligned with those principal axes of curvature we just found. Step 2, this is where the magic happens. We rescale the vector. But, and this is the whole point, we don't shrink everything equally. The amount of shrinkage for each component depends on its corresponding eigenvalue. The components that lie along axes with small eigenvalues, the flat directions of our error surface, get shrunk down the most. A lot. And then, step 3, we just multiply by Q to rotate everything back to where it started.
And that right there is the big reveal. Weight decay isn't just a brute force tool that shrinks everything. It's an incredibly intelligent, targeted process. It uses the geometry of the problem to find the directions where the model is most uncertain, the flat valleys in the error landscape where the data gives very little guidance, and it selectively and aggressively penalizes the weights that correspond to only those directions. It's amazing.
Now, this powerful idea of finding the most important directions in a problem isn't just for regularization. It's the exact same intuition that powers one of the most widely used techniques in all of data science, principal component analysis, or PCA. We can use this same geometric thinking to compress and make sense of massive datasets.
So what is PCA? At its core, it's an algorithm that sifts through a messy, high-dimensional dataset and finds the directions that contain the most information, the most action. These are called the principal components. They're the directions of maximum variance. And by keeping just a few of these key directions, we can often squish a huge dataset down to a much smaller size while losing very little of what actually matters.
And just like with weight decay, we can frame PCA as a mathematical optimization problem. This formula might look a little different, but it's basically asking a very simple question. If I could only keep one dimension of my data, what's the single best line I could project it onto to minimize the amount of information I lose? And it turns out the answer to that question is the direction of maximum variance. It's the first principal component. Once again, it's all about finding the hidden geometric axes that matter most.
Whew. Okay, so we've covered a lot of ground here, from a simple problem of overfitting all the way down into the deep geometry of eigenvectors. So let's take a step back and pull this all together. Let's talk about why this hidden mathematical world is so critical to understand.
So let's trace our path one last time. We started with overfitting, a model that cheats by memorizing. We saw that L2 regularization or weight decay is our weapon against it. But the real aha moment came when we used the tools of linear algebra to see what weight decay really does. It's not just dumb shrinking, it's a precise geometric operation that rescales weights intelligently along the natural axes of the problem itself. And that's the big takeaway here. Linear algebra isn't just about crunching numbers. It's like a pair of glasses that lets us actually see, understand, and even control the hidden geometry of how our models learn.
And that really leaves us with one last big question. We've just peeked into the geometry of a fairly simple setup. But today's deep learning models live in spaces with millions or even billions of dimensions. What other incredible secrets about how these things think, how they generalize, and why they fail are still out there, just waiting for us to find them, hidden in the vast geometry of deep learning?